So we started chapter 13 by introducing a complex number that is written as in Cartesian form as x plus iy, where I is square root of -1. And we said that x is the real part of z and y is the imaginary part of z. And we introduced complex plane that every point on the complex plane represents a complex number, and every complex number has a position in this plane. So it's like a real axis for all real numbers. Here we have a complex plane for all complex numbers. And then we talked about how the complex numbers add or subtract. We said that it looks like a vector, so addition and subtraction. And then the multiplication is different. Multiplication is like multiplying two binomials, and everywhere we get I squared, we replace it with -1. That's why, for example, here we have -y1, y2. So this imaginary part times this imaginary part multiply becomes real. All right, and then cross terms become the imaginary part of the multiplication. And then we define the complex conjugate of a complex number as x minus iy, when z is x plus iy, z bar is x minus iy, which is the complex conjugate of z. And we saw that the z bar is basically sum of the squares of the imaginary and real parts, and therefore z bar is the square of the distance of the z to the origin. So then absolute value of z is defined by the square root of that, and we call it absolute value or modulus of the complex number. And this z bar that we have defined this way has some properties. Basically, it is distributive over summation, subtraction, and multiplication and division. So means that whatever expression you have for z, if you want z bar, just flip the sign of I that you see in there, and it will be the complex conjugate. And the real part can be written as 1/2 of z plus z bar, and imaginary part is 1/2i of z minus z bar. And then using this complex conjugate definition, we now define the ratio of two complex numbers, or division of complex numbers. It is the same as division of binomials, that we make the denominator real by multiplying both numerator and denominator by the complex conjugate of the denominator, and then turns to something like this. So the division of complex numbers are completely definable and very well defined, as opposed to vectors. You cannot define any way that is well defined division of two vectors. Division of two vectors don't exist, but complex numbers, we can divide, we can multiply. It's all the things that we can do with real numbers, we can do with complex numbers. All right. So here was some exercise that we found imaginary part of some values. That's not just an arithmetic exercise. And then we introduced polar form of complex numbers. We said that the Cartesian form, which is x plus iy, shows the two real and imaginary part, like the two components of a vector. But we can also define or represent or identify a real number using the distance it has to the origin, or the modulo of that, or the absolute value of it, and the direction in which it is positioned from positive x direction counterclockwise. So theta again here is in radians. And we can represent this complex number by r and theta. And also we can represent it by x and y. And x and y, x and y are related to r and theta like this. X is r cosine theta and y is r sine theta. And therefore, z can be written as r cosine theta plus I r sine theta, or usually we factor r. And r is the modulus, and it's written like that, as we said. And theta, in terms of the x and y, the Cartesian coordinates, is tan inverse of y and y over x. And then we said that this is not always correct because this is always giving us a angle that is between negative pi over 2 and pi over 2, which is always giving us a direction that is in the first quadrant and the fourth quadrant. But if the complex number is in the second or third quadrant, this doesn't give us the correct value, and we need to add pi to that to get to the right direction. And that, when we can do that, when x is negative, we see that when x is negative, we are in the second or the third quadrant. In those cases, you just add to the value of tan inverse of y over x a pi to get to the correct direction. And also, if you add 2k pi, means the multiple of 2 pi, to any angle, you get the same angle by turning around the circle, right? Multiple times. So these are all the same angle. And this is theta, multiple values for the same complex number. And we call this theta argument of z. And with capital A, when theta is in the first round of the circle. And if you add multiples of 2 pi to it, we call it argument of z with lowercase r, arg of z. So we have the same as arctan, arc sine, and arc cosine that we show with capital for the first one and with lowercase for all of them. This is the same thing. And theta is always from positive x-axis counterclockwise. In order for these definitions to work, this has to be the case. Theta is always from positive x direction counterclockwise, means from this direction going this way positive. If you go clockwise, we can consider it negative. Any questions so far? All right. So then we looked at the multiplication of the two complex numbers in polar form, and we saw that when you multiply Z1 and Z2, that has our absolute value or modulus of R1 and R2, and the angles or arguments of theta 1 and theta 2, then when you multiply, the moduli multiply together, but the angles add. So therefore, we can see that we can write the exponential form. We can represent this polar form in exponential form. It's r e to the I theta, because if you do that, the same thing with this, the r's multiply and thetas add. And then again, we see that the e to the I theta becomes cosine theta plus I sine theta. We called it Euler's formula because Euler was the one who found this out. Another way to see Euler's formula is by looking at the powers of I to the power 2n becomes negative 1 to the n power, which is all plus or minus 1 is real, and I to the power 2n plus 1, which is I to an odd power, becomes imaginary, pure imaginary, either plus I or negative I. And then if you assume that the exponential function can be expanded also for the imaginary exponent, we can write it like that, as we did for the exponential of x, e to the x. Then we can separate these powers of k to even powers and odd powers. And the even powers, I to the 2n becomes negative 1 to the n. So it becomes like that, and theta to the n divided by 2n factorial. And all of these have an I. We can factor the I, and the rest will be negative 1 to the n theta to the power 2n plus 1 divided by 2n plus 1. And you see that this is the Taylor expansion for cosine theta, and this is Taylor expansion for sine theta. So you see that e to the I theta becomes cosine theta plus I sine theta, which is another way of looking at this Euler formula. All right. And then we define the inverse of a complex number by just in the exponential form. It will be a lot more clear. So our inverse e to the negative I theta means that the modulus inverses and theta becomes negative. And therefore, if you want to divide, you get the division of the two moduli and subtraction of the two arguments. And then we define the integer powers of a complex number. It turns out to be like that because of, if you look at the exponential form, r to the n cosine of n theta plus I sine n theta. So when you multiply n of those, r to the n is the argument, but then the angles add n times, so it becomes n theta plus I sine n theta. And then apart from this useful information, it gives us another useful information that says that this cosine theta plus I sine theta to the power n becomes cosine of n theta plus I sine of n theta. That is called De Moivre formula, and this can be used to find the sine and cosine of multiples of theta in terms of sine theta and cosine theta, which is very interesting. Okay. And then we defined the roots. Nth root of complex number becomes the nth root of r, and then cosine of theta over n plus 2k pi over n. This is a multi-valued function. So it means that nth root of a number has n distinct values. All of them, if you raise them to power n, give you w. And all of them are on a circle with the radius of nth root of r, but they are separated by 2 pi over n. And the first one has an angle of theta, which was theta of this z. The first one has an angle of theta over n with k equal to 0. We call it W0, W0. And then we have W1, W2, W3, and so forth until Wn minus 1. So these are the fifth root of 1 plus I. The 1 plus I has an angle of 45 degrees, or pi over 4. And then if you divide that by 5, you get this angle, which is about 9 degrees. And then next one is 2 pi over 5 away from there, and then another 2 pi over 5, another 2 pi over 5, another 2 pi over 5. And then if you do another 2 pi over 5, you get back to what you were before. So you have 5 distinct values. And all of them are on a circle of radius this much. In this case, it is 1.072. All right. And then we said that looking at the nth root of 1s, which is just this equation, you can see that you can write Wk as W naught, which is the first one with k equal to 0. This is W naught. This is W naught with k equal to 0 times omega k, which is this. See, if you multiply these two, what you get is the modulo of this, which is 1 times modulo of that, which is that one. And then the angles add, so it becomes theta over n plus 2k pi over n, which is that. All right, so we can write Wk as W naught times omega 1 to the power k. And omega k can be written as omega 1 to the power k, because omega 1 is when k is equal to 1. So we have 2 pi over n. Omega naught is 1 for all of n root of 1. This is omega naught. This is omega 1, and this is omega 2 for the third root of 1. For the fourth root of 1, we have 1, I, and negative 1 and negative I. And for fifth root of I, we have fifth root of 1. We have 1 and all of this. You see, the first one is called omega, and then the second one is omega squared, because you see, when k is 1 and then becomes 2, then the argument becomes twice as big, right? So becomes the angle from x-axis becomes double. And for omega 3, the angle becomes triple and quadruple and so forth. For n equal to 5, when you do to the power 5, you get back to 1. All right, so for each n, if k becomes n, then argument 2 pi is the same as 0, so get back to 1. So these roots of 1, n root of 1 can be used as omega k to write wk, n root of any complex number, as the first one, which corresponds to k equal to 0, times these omega k that are also omega 1 to the power k. All right, so there's a lot of information you need to think about and absorb it completely. All right.
So WK is just the magnitude of the root, and
No.
omega parts like the actual, like the angle with the portion. So like the magnitude times like the portion of like the angle.
The WK is not, WK is the whole n truth, right?
Oh, I meant W naught. So W naught is like the magnitude.
W naught is not the magnitude. You see, it has.
No.
Yeah, it has some imaginary part, right? It is complex, but it is the first one. For example, if you look at this, W naught is this one between all these 5.
Okay.
What this means is that when you want to get fifth root of I plus 1, there are 5 of them. So you get the 0th one, which is this one, with k equal to 0, and then the rest of them can be generated by multiplying these omega, in this case, omega 1 to the power k. Right? It means that when you multiply this one, this is omega 0, right? You multiply that by this omega, then what you get is this one.
I see.
If
So
you
you're just
multiply
using
by
that, that's your first one to reference, and then they're all just rotated around essentially.
That's right. Exactly.
Okay.
So you get the first one that is, with the, k equal to 0, you find that, and then you multiply them by omega 1 for fifth root of 1. There's omega k, but for k equal to 1, which is this one. And you multiply that number that you find here by omega, and then omega squared, omega cubed, and so forth. You get all of these. You generate all 5 of them. All right. This is what this slide is telling you, basically. You see, omega k is equal to omega naught times omega 1. Sorry, wk is equal to w naught times omega 1 to the power k. Omega 1 is the first root of fifth root of 1.
What will be the next value? I mean, would be maybe W naught, and then
You see,
omega 2.
the first one for k equal to 0 is this for W, right? Then for W1 will be W naught this times
Okay.
omega 1 to the power 1.
Got it.
For the second one will be omega 1 to the second power, and so forth.
Okay, thank you.
You're welcome. All right. So this is why the nth root of 1 is useful if you want, and it is easy to write it down: cosine of 2k pi over n and sine of 2k pi over n. Or in exponential form, it is even easier to write it. I should have actually included that in the this is equal to e to the 2k pi I 2k I over n, right? So you multiply all of these by this one, which is nth root of r times e to the I theta over n. You multiply this by these ones, or this also can be written as the first one, e to the 2 pi I over n to the power k, right? So that you can get this first one, omega w naught, and multiply by these, which is omega 1 to the power k. And then you get all of these values that are here, right? And in exponential form, this can be also written as square nth root of r times e to the power I theta over n plus 2k pi over n, right? So that's what we say is equal to omega naught. Oh, I mix up omega and w. W naught, the first one of the w's, times the second one of the omegas, which is with the index 1, to the power k. That means that the 0th one is the omega naught. First one is omega, sorry. 0th one is w naught. And first one is w naught times omega 1, which is when this is 1, when k is 1 for this one. And then the second and third and fourth is the powers of omega 1. All right, anyway, it's a little bit of thinking requires. All right. All right, let's move on. We define some analytical mathematical analysis, actually, expressions or definitions. We talk about unit circle, open circular disk, which is an open set, like it's circular around any point A in the complex plane. Closed circular disk, which is the open circular disk plus the boundary, which is a circle of radius rho. And then this open circular disk is called the neighborhood of the point A. All right. And then we talked about point set, interior point, open set, boundary point, closed set, complement, and all that. And whenever it comes out, if you don't remember the definition, I will give you the definition later. And a domain is any open and connected set. A region is an open and connected set, that is a domain, plus some of its boundary points. So this is a distinction in this book, that by domain, it means an open set. By region, it means that open set and some of its boundary points. All right. So these are some basic definitions, and then we're going to define complex functions. What is a complex function? A complex function W is a function of Z. We call it f of Z. And it has two parts. Real part, this is the real part of the function. This is the imaginary part, like the numbers that have real part and imaginary part. But in this case, each one of the real and imaginary part of the function is itself the function of x and y, which is the real and imaginary part of Z. All right. So this is when Z, of course, is x plus iy. So u is a function of Z, means that it is function of x and y, and v is also a function of Z. U is the real part of the function, V is the imaginary part of the function. But each one of them are functions of X and Y, which are like two variable functions. And then this is the function, and then we want to define what the limit is. See, we're going to, you're going very fast through all the complex analysis because it's very, very similar to what we have in real analysis, real functions and limits and derivative and integral, all of that. So we're going to push through all of these. And whenever there is a big difference, we're going to address that. But for the things that are very similar to real functions and real analysis, we just introduce you because you already know the real analysis. And so this is very similar. So limit, what is a limit? We say that the limit of a function f of z as z approaches z naught is L, and we write this limit of f of z as z approaches z naught equals L. If and only if this situation it holds. For example, we say that if z approaches, basically it says z approaches z naught, then f of z approaches this L. This should be also capital L if this is capital L. All right. So this is basically it. But in technical terms, to be mathematically accurate and very precise, we have this sentence that you see in a real analysis. We said this limit is L if and only if for every epsilon positive, no matter how small, there is a delta positive, such that if z is in the neighborhood, the delta neighborhood of z naught, means if z is in this neighborhood, then f of z is in the epsilon neighborhood of L, right? This is the epsilon neighborhood. This should be epsilon, right? So why do they say that? Say that, okay, we say the limit of f of z is L. What we mean is that f of z can get as close as much as you want to the L. All right, as close as you want. So you introduce an epsilon. You say, okay, I want L to be so close to L, because we don't say f of z is exactly L. We say it approaches L. So say how close do you want it? You say I want it a billionth of a unit. Okay, you give me an epsilon. I introduce a delta. I said if you make this neighborhood of z naught this big with introducing the delta, giving you the delta, then I guarantee that f of z is that close to L. So that's why it says for every epsilon positive that's given, no matter how small, there's a delta greater than 0 such that if z is in the delta neighborhood of z naught, means if this is here, then f of z is in the epsilon neighborhood of L. All right, this is how in real analysis they use it, but in real analysis you can approach this z naught or x naught only in two ways, from above or from below, right? That's why we have a left limit and right limit. But here this z can approach z naught in many different ways, infinitely many different ways. And for every way, which way that it goes to z naught, this f of z should approach to L. All right. So the definition is similar, and this is the reason it is defined like that. But we are not going to do anything with this. I just want to note that this is very similar to what you had in real analysis. So, and then what is continuity? The same way as we had, we say that the complex function f of z is continuous at z equal to z naught. If f of z naught is defined, means f of z naught exists, And also, limit of f of z as z goes to z naught equals to f of z naught. This is exactly the same as real analysis. All right. So we say the function is continuous if the limit is the same as the value of the function at that point. Does that make sense? Any questions? And in real analysis, we say that the limit exists if the left limit and right limit exist and they are the same. Here, we don't have two approaches, left and right. We have infinitely many approaches, and for all of them, they should match. And especially if you go in two directions in match, in all directions it will match. Okay. For continuity in a region, we mean the complex function fz is continuous at every point in the region. So the complex function f of z is said to be continuous in a region of f of z if it is continuous at every point in the region. And now we want to define derivative of a complex function. So you see in analysis, we first define limit, and then we define continuity, and then we define derivative. Here we are doing the same thing. What is the derivative of a complex function? Derivative of a complex function also defined similar to real functions. It is equal to this. So we say f prime of z is the limit of this fraction as delta z goes to 0. The fraction is the increment in f, means f of z plus delta z minus f of z, means that how much f of z changes if you change z by delta z. Divide by the delta z itself. So that's naturally the same as, remember, f prime of x is limit of f of x plus delta x minus f of x divided by delta x as delta x goes to 0. This is exactly the same. But of course, in this case, delta z, in this case, delta x is can be positive, negative, but delta z can be in any direction. That's the difference. Or there was another definition kind of like this: f prime of z naught is limit of f of z minus f of z naught divided by z minus z naught. This is similar to saying f prime of the derivative of function at a particular point x naught is the limit of f of x minus f of x naught divided by x minus x naught. This is the increment in the function divided by the increment in the variable when x approaches x naught. We have these two definitions that are exactly equivalent. Now we have the same for the complex functions. And then from these definitions, there comes the differentiation rules. We see that if a constant times a function you use to take a derivative, it becomes the constant times the derivative of the function. So cf prime becomes cf prime. And then derivative is linear, means that f plus g prime is f prime plus g prime. And also we have a multiplication rule, exactly the same as the real function or product rule. Fg prime, Fg quantity prime is f prime g plus g prime f. The derivative of first one times second one plus the derivative of the second one times the first one. And also we have a quotient rule. F over g prime is f prime g minus g prime f divided by g squared. So all of these come from the definition. We are not proving that. But then z to the n power derivative becomes n times z to the power n minus 1. Exactly the same as what we had in real analysis. All right. And when n is integer. So there are some examples. For example, here, f of z equal to z bar is not differentiable. Is not differentiable anywhere. It is really hard to make a function in real analysis that is not differentiable anywhere by discontinuous. Here, this z bar is continuous, but it's not differentiable anywhere. We are going to show that to see how this differentiability works. All right. So as we have this definition, f prime of z is limit of f of z plus delta z minus f of z divided by delta z approaches to 0. So we want to now put f of z equal to z bar. That means f of z plus z bar means, sorry, f of z plus delta z is z plus delta z bar, and then minus z bar divided by delta z. So this becomes z plus delta z bar minus z bar divided by delta z. And you know that when you have the complex conjugate of a summation of two numbers becomes sum of the complex conjugates. So we can write that as z bar plus delta z bar minus z bar, and now z bar cancels. So becomes limit of delta z bar divided by delta z as delta z approaches 0. Now, this delta z can approach 0 in different ways, right? So this is z here, and z plus delta z here, right? This is delta z, and then this delta z can approach 0, or z approaches this z naught, if in two different ways, along path 1 or path 2, can go this way or can go this way to 0. Okay, and now we see what happens if it approaches in each direction. So along path 1 means that you first put the delta z, delta z is equal to delta x plus I delta y. So along path 1 means what? Means first you put delta y equal to 0, and then make delta x go to 0. All right. So so delta z, when you get close here, you already put delta y equal to 0, so delta x becomes just delta x, right? And then when delta z is delta x, what is delta z bar? Means the complex conjugate of delta z. So in this case, delta z is real. The complex conjugate is the same as delta x, and therefore delta z bar over delta z is 1, and the limit of it becomes 1 as delta z goes to 0 along path 1. But if you go along path 2, first you put delta x equal to 0, and then make delta y go to 0. So delta z is I delta y. And the complex conjugate of that is delta z bar, which is negative I delta y. And then the limit of delta z bar over z, delta z becomes negative I delta y divided by I delta y, becomes negative 1. So you see that if you go at different paths along these paths 1 and 2, the limit is different. It's the same as, the limit of left limit and right limit in real analysis is different. So if the limit exists, it should be the same in all different directions, no matter how you approach the limit, right? Here we show that it changes from 1 to negative 1 if you go from path 1 or path 2. Therefore, the limit doesn't exist. This limit doesn't exist. The limit is the derivative, therefore the derivative doesn't exist. So we say that this function is not differentiable because this limit doesn't exist. Okay? Does it make sense? Any questions? All right. All right, let's continue. This is what I just said. Now we're going to talk about analytic functions. So we defined limit, defined continuity, we defined the derivative, and now we want to say what is analytic function. Complex analysis deals with the analytic functions and that are functions that are differentiable in some domain. Analyticity is defined this way. A function is said to be analytic in a domain D if f of z is defined and differentiable at all points of D. All right, so we found out what differentiability is, means that those limits exist in all points in a domain D. Therefore, we call a function that have this property analytic functions. The function f of z is said to be analytic at a point in D if f of z is analytic in a neighborhood of z. At a point z, I should say, yeah. At a point z in D if f of z is analytic in a neighborhood of z, that is in D. All right, you know, if it is a domain, it's an open set, right? This is domain. It's an open set, means every point of this is an interior point, remember? And therefore, interior point means that there is at least one neighborhood of this point that is inside the domain. And we said that the function f of z is said to be analytic at a point in D, point z in D, if f of z is analytic in a neighborhood of z that is inside D. All right, that's why we had all these definitions, the interior points and all that, and open sets and all that. By analytic function, we mean a function that is analytic in some domain. When we say just analytic function, we say that there is a domain where that function is analytic in it. And we know that polynomials and rational functions are mostly analytic. The non-negative integer powers of z, which is 1, z, z squared, z cubed, and so forth, are analytic in the entire complex plane. And so are polynomials. Polynomials are a combination of all of these up to a z to the power n. So this is a polynomial because 1 in here is analytic, z is analytic, z squared is analytic, and so forth. We say that this combination is analytic. So this actually covers a whole category of all complex functions. So they are all analytic in the entire complex plane. So analytic everywhere. And also a quotient of two polynomials, g of z and h of z, is called the rational function, f of z equal to g of z over h of z, similar to real functions. We said that this is rational function, and this is also rational, this is also analytic everywhere except that when h of z becomes 0. A rational function is analytic at all points except where h of z is equal to 0. Again, the same as real analysis. All right. So this already takes care of a huge class of complex functions, that all polynomials are analytic and all rational functions are analytic except that where the denominator is 0. So far, so good. In that is a large category of analytic functions. All right. All right, that's that for section 13.3. All right, so we defined what the analytic functions are, and then we're going to go to section 13.4, where we talk about now the for analyticity. These Cauchy-Riemann equations show that when a function, a complex function, is analytic. The complex function W, which is the function of z, and it has a real part, imaginary part, as we noted, is analytic in a domain D if and only if the first partial derivatives of u and v satisfy the two Cauchy-Riemann equations. This is in one of the equations, ux equals to vy. What does it mean? Means the partial derivative of u with respect to x should be equal to partial derivative of v with respect to y. This is one of the equations. And also partial derivative of u with respect to y should be negative of partial derivative of v with respect to x. These are two Cauchy-Riemann equations, and we said that the function is analytic if and only if these two are satisfied. Means that it's very easy. So if you want to see a function is analytic, you just check these two. If both of these are valid or holds, then the function is analytic in that domain. So ux is partial of u with respect to x, uy is partial of u with respect to y, and so forth. All right, so where does this come from? When I was studying, I didn't pay attention to the proof, or the proof was not given to me. So I was always wondering why the hell is that? But now I can show you where they come from. All right. This is the definition of derivative of function f prime of z. As we said, this is basically f prime of z equal to limit of f of z plus delta z minus f of z divided by delta z as delta z goes to 0. But it is delta z and delta z are written in terms of x and y, and f is written in terms of u and v, the real part and imaginary part. You see, this is f of z plus delta z, right? Because it has u plus iv, but u is evaluated at x plus delta x and y plus delta y, and v also is evaluated at x plus delta x and y plus delta y. And the next one is u of x and y plus iv of xy, which is f of z, right? So f of z plus delta z minus f of z divided by delta z, which is delta x plus I delta y. Okay, so this is by definition the derivative of the function at point z, and we want this to be, we want this limit to exist. Therefore, we say it shouldn't matter whether we are going to approach from z plus delta z, approach z along path 1 or approach z along path 2. What happens if we approach z along path 1? That means that we put delta y equal to 0, delta y equal to 0, and then delta x approaches to 0. Okay, so if we do that, is delta y becomes 0 everywhere, right? And then what we get is this: u evaluated at x plus delta x and y, and v evaluated at x plus delta x and y minus u plus iv divided by at x and y divided by delta x. So this is the category. So the first part, you see, if you gather this u and this one, so you get u of x plus delta x and y minus u of xy divided by delta x as delta x goes to 0. And then for the next part, because this is also 0, you have both of these, it means these two. Now, if you put together these two, I can be factored. You have v of x plus delta x and y is 0, right? V of x plus delta x and y minus v of xy divided by delta x. So I can be factored and the limit distributes. So it becomes limit of this and limit of that, right? But there's an I here. I is the factor for both of these in here. So we just factor the I, and it is a constant, comes out of the limit. And now you look at these limits. What is the first one? Limit of u plus u at x plus delta x minus u at x divided by delta x when y is kept constant as delta x goes to 0. Do you recognize that?
So it's the partial of y
That is partial.
z in terms of x.
Sorry.
It's ux, right?
Yes, it is partial derivative of u with respect to x. That's correct. So this is ux, means partial derivative of u del u over del x. And this one is partial derivative of v with respect to x. So del v over del x. So this f prime becomes like this. ux plus I vx, right? Now we're going to approach z from the second route. So if you go this way, what happens? In this case, you have delta x put equal to 0 first, and then delta y goes to 0. If you put delta x equal to 0 in this equation, so this goes over, this goes away. So all of these delta x's go to 0, and then delta y approaches 0. So you can see that when this delta x is 0, you have u of x and y plus delta y. And then here you have u of x and y with negative sign. That's the real part, divided by iy when delta y goes to 0. And then the rest of it will be I, and there's I in the denominator. V of x plus x and y plus delta y minus v of xy divided by I delta y. So you see that this I in here cancels out, and the rest will be partial derivative of v with respect to y, right? And here you can bring I outside. 1 over I becomes negative of I, and then become negative I times partial of u with respect to y. All right, so it becomes partial v with respect to y minus I partial of u with respect to y. All right, minus I partial of u with respect to y plus partial of v with respect to y. All right, so if you go this way, you get this. If you go that way, you get this. But in order for the limit to exist, these two should be the same. Therefore, say the real part should be the same, the imaginary part should be the same. So this should be equal to that, and the vx should be equal to negative uy. So vx should be equal to vy, ux should be equal to vy, and vx should be negative of uy. All right, so that is where these Cauchy-Riemann equations come from, by applying the condition that these limits should exist no matter how you approach. And of course, if you approach the z from z plus delta z, approach z, or make delta z go to 0 from these two paths, and they match, the limit exists, you can argue that it will exist in any different way, any other way. All right. So this is proof of Cauchy-Riemann equations. Any questions?
Yeah, I'm still confused on how you made delta y equals 0 and delta x approach 0 on the first part and the other condition on the second part.
All right. Yeah, I understand. You see, from here, you want to go to here. You said that we can go at different paths. In particular, we can go this way. Going this way means that we set delta y equal to 0 first, make delta y 0, absolutely 0, and then approach delta x to 0. All right, so then this delta y goes to 0, you can set it equal to 0, and then make this, instead of delta z going to 0, is delta x goes to 0. Then becomes these two.
Is that because like when we solve for limits, sometimes you can like directly substitute whatever the term is approaching for calculating the limit. So we do that for one of them, and then we follow the convention for the rest for the other term. Like
Yes,
because delta y, delta x is delta z, right? And we want
yeah,
delta z to be 0, but we can't sub in 0 directly. So we do
Yeah,
one of them
you
and then
can't-
approach for the other.
that's right. You can't put the delta z equal to 0, but you can put one part of it, delta y equal to 0, because it's delta z is not 0 yet, right?
Right.
You can, so that means that going to z from this path 1 by putting delta y equal to 0 first, going through path 1. But then if you go through path 2, means that first you put delta x equal to 0 and then approach delta y equal to 0. Approach delta y to 0. All right. We're not putting z equal to, we're not putting delta z equal to 0 because that's forbidden. Delta z cannot be 0 in the it is in the denominator. All right, but we can approach it to 0. So for the first one, we put equal to 0 because it is just one part of delta z. We're not making division by 0, so it is allowed. For the second one, we do the other way. We put delta x equal to 0 and then approach delta y to 0. So this is going along two different paths. And I don't know if I answered your question or not, but then if we say the condition for these two limits from two different paths to be the same leads us to these two conditions. All right, did I answer your question?
I think I just gotta come to office hours.
Okay.
Yeah, thank you.
If you feel that it is still unclear, I can explain more, but it is pretty much it. In this way, we put delta z equal to 0 first, and then approach z from the right. But in this case, we put delta x equal to 0, we approach z from above. And the limits turn out to be this way and this way. And in order for them to be the same, we have to have these conditions. So that leads us to a condition, very good conditions, to figure out whether a function is analytic or not. All right?
Professor, one question.
Yes.
Is this related for electrical circuits?
Electrical circuits.
Yeah, what kind of flow is this one?
Flow?
Yeah, like the green arrows. So I know those are the limits, but representing any kind of flow or something? Or
I can't relate to that. I'm not a specialist in circuits. It might have some. I can't relate it to circuits right now.
okay.
Yeah, sorry. That's not my specialty. I don't know circuits that well. Maybe. All right.
Yes, yes. Fine.
All right. Let's go.
Thank you.
No problem. So this is an example. This is we want to see if f of z defined by this function e to the x cosine of y plus I sine y analytic or not. So we say that the real part of this is u of xy, which is e to the, we want to see if it satisfies the Cauchy-Riemann equations. So u is the real part, which is e to the x cosine of y. And v is the imaginary part, which is e to the x sine of y. And then we can check to see if these satisfy the Cauchy-Riemann equations. So we calculate the partial derivative of u with respect to x, which becomes itself because it's e to the x, right? And partial of u with respect to y becomes negative e to the x sine y, because cosine of y becomes negative sine y. And then partial of v with respect to x becomes also e to the x sine y, and partial of v with respect to y becomes e to the x cosine y. And now you see that these two are the same, ux and vy are the same. And uy is negative of vx. So you see ux is vy and uy is negative of vx. So the two Cauchy-Riemann equations are satisfied. Therefore, fz is analytic everywhere in complex plane. You see that? So this is a complex function. We see that it satisfies the Cauchy-Riemann conditions everywhere in complex plane. Therefore, the function is analytic everywhere in complex plane. Make sense? All right, so now we want to talk about Laplace equations. If f of z is analytic in a domain D, then both u and v, which is the real part and imaginary part of z, f of z, satisfy Laplace equation. You know Laplace equation, remember? Laplace equation was this, del squared of u is equal to uxx plus uyy, means second derivative of u with respect to x plus second derivative of u with respect to y equal to 0. Remember, del squared of u was del dot divergent, del dot gradient of u. And gradient of u, del was this, del over del x, del over del y, and also del over del z, but we are two-dimensional here. Dot, again, del over del x and del over del y, right, of u. So first you do the first one, it becomes del over del x and del over del y. Then dot this, which is del u del x and del u del y. This is the gradient of u, and then the divergence of that is again del over del x of del u over del x, which is del squared u over del x, and plus this, because divergence, it is dot product plus the second derivative of u with respect to y. So that is uxx plus uyy. All right. So this is, we say that if the del squared of something is equal to 0, we call it the Laplace equation. Remember, when it wasn't 0, we called it Poisson equation. But this is Laplace equation. So del squared of u is equal to 0, and del squared of y, v, is equal to 0 as well. So both of u and v satisfy Laplace equation. So if the function is analytic, all right? So proof of this is this. This is the proof. Suppose that the function is analytic. So we have ux equal to vy. and uy equal to negative vx. That is Cauchy-Riemann equation that says that if they are satisfied, the function is analytic and vice versa. So if the function is analytic, we have these conditions. And now we take the derivative of the first equation with respect to x. So it becomes uxx equal to vyx. And then we take the derivative with respect to y of the second one. So uyy becomes negative vxy. And vxy and vyx is the same. And if you add these two equations, you get what? You get uxx plus uyy equal to 0. Right? And now if you take the derivative of the first equation with respect to y, then you get uxy equal to vyy. And take the derivative of the second one with respect to x and also multiply by a negative sign, become vxx equal to negative uyx. Okay, and then if you add these two, you see that these two are the same but opposite. They cancel out. If you add the two equations, then vxx plus vyy equal to 0. So these means that the u and v satisfy Laplace equation. Okay, this is the proof of this assertion. All right. Solutions of Laplace equation having continuous second order partial derivatives are called harmonic functions. Is when this equation is satisfied by u, we say u is a harmonic function. And their theory is called potential theory. Why is it called potential theory? Because in physics, remember, we had the potential function that was the derivative, the line integral of the electric field, and we say that therefore electric field can be written as negative of gradient of a function which we call potential function. And if you take divergence of E is divergence of negative gradient of phi. Negative comes out, becomes negative del dot del phi, becomes negative del squared of phi. All right, so the electric field is del squared of phi, and it is in general equal to del squared of phi becomes rho over epsilon naught, but in free space it is 0. So you see the Laplacian of the potential function in physics is 0 in free space. That's why when this is called a function is called, the function satisfies Laplace equation, which is the squared of that function is equal to 0. We call it a potential function, and the theory behind it is called potential theory. All right, so that's the story behind this potential theory. Okay, and the real and imaginary parts of an analytic function are harmonic function because we just said that they satisfy the Laplace equation. And if two harmonic functions u and v satisfy the Cauchy-Riemann equations in the domain D, they are the real and imaginary parts of an analytic function f in D. So if you have two harmonic functions satisfy Cauchy-Riemann, they have to be real and imaginary parts of an analytic function. Then v is said to be a harmonic conjugate function of u in D. So this is harmonic conjugate. This when they satisfy two functions u and v satisfy Cauchy-Riemann equations, they also satisfy Laplace equation. So they are harmonic functions. and they are real and imaginary part of a analytic function. Therefore, they are called harmonic conjugate of each other. All right. And this conjugate, the book emphasizes that this has nothing to do with the complex conjugate, Z bar. This is harmonic conjugate. It's very different from complex conjugate, okay? So harmonic conjugate means that two functions that together satisfy the Cauchy-Riemann equation, because Cauchy-Riemann equation involves two functions, u and v, okay? So this is about harmonic conjugate functions, and here is an example. Any questions? I think the example makes it more clear. Verify that u equal to x squared minus y squared minus y is harmonic in the whole complex plane, and find the harmonic conjugate function v of u. All right, so first we want to see this is a harmonic function. How do we know it is a harmonic function? We said that it is harmonic if it satisfies Laplace equation. And Laplace equation was del squared of u, which was uxx plus uyy equal to 0. So let's find out if uxx and uyy add up to 0. What is ux? Means derivative of u with respect to x. These are just don't have x, it becomes just 2x, isn't it? And then uxx becomes 2. What is uy? Uy becomes negative 2y, right? Negative 2y minus 1. And uyy is another derivative with respect to y, becomes negative 2. Therefore, you say uxx plus uyy, which is 2 minus 2, becomes 0. So del squared of u is equal to 0. Therefore, u is harmonic. Make sense? And now we want to see, okay, what is the harmonic conjugate of u, which we call v? If u is this function, what is its harmonic conjugate? So here is the solution printed out. Ux is 2x, uy is negative 2y and minus 1. Uxx is 2, uyy is negative 2. Then del squared of u is equal to 0. And the partial derivatives are continuous everywhere. So now what is v? If you want to find v, you know that v is harmonic conjugate of v, therefore vy should be equal to ux, right? So ux was what? Ux was 2x. And therefore, v, if you take antiderivative here, we get 2xy. V derivative with respect to y of v is 2x. So v should be 2xy. If you take derivative with respect to y, you get 2x. But it can be plus a constant as far as y is concerned. So it can be a function of x, right? If you take derivative with respect to y of this, you get 2x, right? So this is the most general form of v, right? And then you need to have vx equal to negative uy, right? So uy is this. Negative uy is 2y plus 1. And now, if you want to see what v is, you take antiderivative with respect to x. So v is equal to 2yx plus x, right? Plus a constant. So, and these two should be the same. So h of x should be x plus c. So h of x is x plus c. Therefore, v is in both cases is the same, 2xy plus x plus c. And now you can take this and this u, and you see that they satisfy Laplace equation, right? Because ux becomes 2x, vy also becomes 2x, and uy becomes negative 2y minus 1, vx becomes 2y plus 1, which is negative of each other. Okay. So you see that, so u and v are harmonic conjugate of each other. All right. And also you can show that we said that if they are harmonic conjugate of each other, they should be a real and imaginary part of a analytic function. You can also find the analytic function here. All right, so let's write this in this form. Vy equals ux equal to 2x, and vx equal to negative uy equal to 2y plus 1. So v becomes 2xy plus h of x, vx becomes 2y plus h prime of x, which is 2y plus x, then h prime is 1, h is x plus c. And then v becomes 2xy plus x plus c. So this is v. And now we want to see what function, what analytic function is it that this u and v are its real and imaginary parts. So analytic function is f of z equal to u plus I v, right? X squared minus y squared minus y plus I 2xy plus x plus c. That's u plus iv. So we can write this in this way. We can put these two together, and you see that x squared minus y squared plus 2xyi is z squared. So this part is to put together, and then you have ix minus iy, which you can write as I squared y plus ic. And then you see that this is z squared, this is iz, and this is ic, a constant. So it becomes z squared plus iz plus ic. Right? It's a quadratic function. It's a polynomial of degree 2. The coefficient of z squared is 1. Coefficient of z is I. It can be any complex number, and a constant I times c. All right. So this is the function whose real and imaginary parts are u and v that we have here. All right. Any questions? So we're talking about the harmonic functions and harmonic conjugate and what relationship they have. They satisfy Cauchy-Riemann equations. Therefore, they are real and imaginary parts of a complex function, an analytic complex function. All right. Any questions? I didn't give you a break today. exponential function. So this was 13.4. Now in 13.5 and 13.6, we're going to talk about different functions in complex functions, different complex functions. The first one we introduce is exponential function. Exponential function is defined as this: e to the z, which is e to the x plus iy, equal to e to the x times e to the iy, which is cosine of y plus I sine y. Remember, this is the function that we just checked that it is analytic everywhere, because it's at the real part and imaginary parts satisfy Cauchy-Riemann equation. So e to the z defined this way is analytic everywhere. The properties of exponential function are these: if a real for a real z, which is equal to x, e to the z is equal to e to the x. So far so good. If you put y equal to 0, sine of y becomes 0, cosine of y becomes 1, so we get e to the x, right? So far so good. It changes to the real exponential function that we know. And the derivative of e to the z becomes e to the z itself. How do we know that? We can take derivative. Remember, we said that if derivative exists, we can approach either way. We can take derivative with respect to x of that, which is the same as derivative with respect to z of this. So derivative with respect to x of that will be e to the x cosine of y plus I sine y. Right? So derivative of e to z is equal to e to the z. So it has derivative equal to itself. And also it has this property, e to the z1 times e to the z2, because e to the z1 plus z2. How is that? Because you see e to the z1 times e to the z2 equals e to the x x1 plus I y1 times e to the I can write e to the x1, e to the x2 times cosine of y1 plus I sine y1 times cosine of y2 plus I sine y2. And we know that this becomes e to the x1 x plus x2. And multiply by cosine of y1 plus y2 and I sine of y1 plus y2. So you see that this becomes e to the x1 times e to the x2, and this one becomes e to the I y1 plus y2, and then you see that becomes e to the x1 plus x2 plus I y1 plus I y2, so it becomes e to the x1 plus I y1 plus x2 plus I y2. So it's z1 and z2. That's e to the z1 plus e to the plus z2. So it has this property. All right. And e to the z can be written as e to the x plus I y. And so e to the become e to the x times e to the I y, and therefore can be written as e to the x times cosine of y plus I sine y, and therefore e to the iy is cosine of y plus I sine y, which is the Euler's formula as we expect. All right. And the polar form of complex functions, this is the book talks about this right here, but I talked about that before. as you remember. So this can be written as r e to the I theta, right? Because yeah, because we have Euler's formula now, all right? So this becomes r, and then cosine theta plus I sine theta becomes e to the I theta. Then we can write z in that form, which we saw that before. All right. In a special case where r is 1 and theta is 0, we can if z is equal to 1, means that r is 1. No, if z is equal to I, yeah, if z is equal to I, no, I think what I'm want to say is if z is equal to -1. If z is equal to -1, what do we have? R is equal to 1 and theta is equal to pi, right? Because -1 is here. We can write this as the distance 1 and the angle pi. So -1 can be written as 1 times e to the I pi, right? Or e to the I pi. And then e to the I pi plus 1 becomes 0. This is a very interesting formula in complex numbers that has all the special numbers in mathematics in it. 0, 1, pi, I, and e. Is a lot of mathematicians love this because it is a relationship between all the special numbers in mathematics. E to the pi I plus 1 equals to 0. Okay, so this is about exponential function, and it is an analytic function. More properties of exponential function are these. First of all, e to the ix. E to the ix, or any x, is cosine of x plus I sine x, which is the square root of cosine squared of x plus sine squared of x, which is 1. So the absolute value of e to the ix is 1. Therefore, absolute value of e to the z, which is the absolute value of e to the x and e to the iy, right? Which is the absolute value of e to the x times absolute value of e to the iy. Here it should be y to be less confusing. And then this one is 1. Therefore, this becomes absolute value of e to the x, which we know is e to the x because e to the x is positive. So absolute value of e to the z is e to the x, or modulo of e to the z is e to the x. X is the real part of z. All right. So argument of e to the z is y, but you can add the multiples of 2 pi to it, because cosine of, you see, e to the z argument of e to the z is actually theta or y, because it is argument of e to the z is the angle of e to the z, right, which is theta, and or it is y basically. Why is it y? Because it is e to the x. It's e to the x is the r, is the modulus, and then argument is right. So this is the modulus. This is the argument, the theta, which is y, and you can add to this argument a multiple of 2 pi, because cosine of y plus 2n pi is the same as cosine of y, and the same for y. Therefore, argument of e to the z is y plus or minus 2n pi for n equal to 0, 1, 2, 3, and of positive integers or non-negative integers. All right. So there's a period, e to the z is periodic with 2n pi I or 2 pi I. So e to the z is periodic with the period 2 pi I. Means that you can add any n times this to z and you get the same number, right? So it means that e to the z plus 2n pi I equals to e to the z. Why? Because the sine and cosine have the period of 2 pi, right? And this, when it is multiplied by I, it goes to argument of sine and cosine, and they give you the same thing for 2n pi if you add it. So e to the z is a periodic function with the period of 2 pi I. So the infinite strip from negative pi to y equal to negative pi to pi is called the fundamental region of e to the z, because if for all of these values, when y is between negative pi to pi, you have a certain value for e to the z, but then if you go from this point to this point corresponding to the next strip, you get the same thing, and then you go 2 pi further, you get the same thing. So this the period is 2 pi I, right? Means that you go up in the y direction, multiples of 2 pi, you get the same value. And that's why we call this one that is in the first in complex plane. Basically, the first period of sine and cosine, you call it fundamental region of e to the z, because the other ones will be the same. All right. Any questions? Today's lecture is not very interactive. So let me ask you some questions. We'll see if we can figure this out. Write the following complex numbers in polar exponential form. Z equal to r e to the I theta. How can we write -1 in terms of r and theta like that? I already did that.
E to the I pi over 2.
I pi over 2.
Just I pi.
Yeah, the angle is pi, right? From positive x-axis, positive real axis. Yes.
Pi, yeah.
E to the pi I. But that is all. You can add
Cosine of pi.
cosine.
No, it would just be sine of pi, right? I
Oh,
sine
cosine.
pi.
No, this is cosine of I pi. This cosine of pi plus I sine pi, which is 0, right? So that's negative. But I'm saying you can write more. You can write because exponential function is periodic, right? So you can write more of these because it is.
Okay, I got that. So it's e to the I pi plus 2n pi.
2n pi I. Yes, very good. So negative pi is another one, but you can add any. You can add e to the I pi plus 2n pi I. So you see, if, for example, if n is -1, becomes this one. If n is 0, becomes, sorry, if n is -1, becomes this one. If n is 0, becomes this one. If n is 2, becomes 3 pi I, right? And so forth. So any odd number of pi times I will be -1. And how do we write I in this form?
Um,
Now it's the e to the I pi over 2.
E to the I pi over 2.
Yes, plus 2n pi.
Yeah, all of them you can add 2n pi I also. What about negative I?
So e to the I negative pi over 2.
Yes, or 3 pi over 2 or negative pi I over 2, right? Again, to any of these, you can add a multiple of 2 pi. What about 1?
and that just be 0 or 2 pi, so 2 pi, and
Yeah.
so e to the I 2 pi n.
Yeah, e to the I 2 pi n or e to the 0, right? 2 pi, 2n pi, you see all of these. This is when n is 0 becomes this one. When n is y becomes this 1 becomes this one, and it can be 4 pi I or 6 pi I or negative 4 pi I, negative 2 pi I, and all of that. Okay, so I guess you get it, right? What about 1 plus I? How do you write 1 plus I in terms of in exponential form?
It's the square root of 2 times e to the I times pi over 4.
That's right, very good. Yeah, square root of 2 because the modulus, remember, I plus 1 is here. The distance is the square root of 2. The angle is, this is 1 plus I. The angle is pi over 4. So we get a square root of 2 e to the I pi over 4. Oops. All right. What about 4 plus 3i? So again, this is the 1, 2, 3, 4, and 1, 2, 3. That number is here.
Okay, so it's gonna be 5 times e to the
Yeah.
I
Yes. What is the
sine
angle?
of cosine of like 4 over 5.
Exponential. You want to write in exponential form. So
Yeah. 5 times e to the I times arc cosine of 4 over 5. So
for arc cosine, yes, or you can say tan inverse. This is tan inverse of, see, this is 3 over 4. So this is tan inverse of 3 over 4. And you can write that in radians. So becomes that 5 e to the 0.6435 I. That 6.6435 is tan inverse of 0.6435 is tan inverse of 3 over 4. Right? Of course, you can add 2n pi as well. 2n pi I. So what about 2 minus 3i? Again, look at it.
So that would be,
Square root of 13 e.
yeah, square root of 13 e to the, let's see.
Yeah.
2 over -3. So negative 0.588.
Okay, yes. But
Or if you do the other angle, I guess you could.
point, let me see it. This is
Oh, 3 over 2. I did the wrong one.
no, it's 2 over 3.
Yeah.
Should be 3 over 2. Yes. It's almost 1 radian, 0.98, negative 0.98. So almost negative 1 radian. Right?
Yeah.
And the other one, the negative 2 plus 3 becomes square root of 3. You see here, we have this number, negative 0.9828, is tan inverse of negative 3 y component over the 2 x component. All right, and we leave it as it is because x is positive. We are in this fourth quadrant, and it gives us the correct direction. But for this one, where are we? The x is negative. You see, we are here, negative 2 and 3. So we are in the second quadrant, right? So the angle is this. But when you calculate tan inverse of 3 over negative 2, your calculator doesn't distinguish between this and that, right? Doesn't distinguish between this direction and that direction. Therefore, you need to add pi to it. So that's why we calculate negative 0.9828 plus pi, because it is in the second quadrant. And x is negative. You see, this x is negative, we add pi to it. So this is very important. If you don't add pi, it is the wrong answer. See, if you don't add pi, it becomes negative 2 minus 3i. But this is negative 2 plus 3i. It's negative of that one. It's not the correct number, right? So be careful about this. Whenever x is negative, you add pi to the result, of tan inverse. Okay, that's why I wrote it is tan inverse theta is tan inverse of y over x plus pi if x is negative. Remember?
Yeah.
If x is positive, you just leave it as that, like what we did in here. But if x is negative, then you need to add pi to get to the correct direction. All right. All right. Let's solve this equation. E to the z is equal to 3 plus 4i. How do you find z?
We make the right side in terms of exponential form.
Mm-hmm. So you
Compare the power.
say that again.
We make the right side become the exponential.
Oh yes, you write the right side as exponent, and then you match the argument of both sides and the module of both sides. Very good. Yes. So we write e to the z as e to the x times e to the iy, and 3 plus 4i as 5 e to the 0.9273i. The 9273 is the argument, which is tan inverse of 4 over 3, right? And we don't add pi because the x is positive. So if you calculate in your calculator tan inverse of 4 over 3 in radians, it will be 0.9273 radians. So it will be like that. And then this e to the x should be 5, or you can write 5 as e to the ln of 5, becomes like this. And therefore, we said that if these two are the same, therefore, the modules should be the same, the arguments should be the same. So the x should be ln of 5, and y should be that, but there's a little bit of complication because you need to add 2 and pi to it, right? So z becomes x plus iy, which is ln of 5 plus 0.9273i plus 2n pi I. See, again, because exponential function has a period of 2 pi I, you can add multiples of the period to this solution. And if you don't write that, you're not considering all of the solutions, okay? Any questions? All right. Then we can, from the exponential functions, we can basically define the trigonometric and hyperbolic functions. Remember that e to the ix is cosine of x plus I sine x. And then if you take complex conjugate of this, e to the negative ix is what? It's cosine of x minus I sine x, right? And then if you add these two equations, these two signs cancel, and you get 2 cosine of x. So cosine of x can be written as e to the ix plus e to the negative ix divided by 2. So cosine of x is 1/2 of e to the ix plus e to the negative ix. And sine of x is, if you subtract these two, e to the ix minus e to the negative ix, cosines cancel, and then you get 2i sine x. And then if you divide by 2i, then you get sine. So sine x becomes 1/2i e to the ix minus e to the negative ix. Make sense? So these are the cosine and sine functions that with real x. X is real in here. But we can define cosine of z and sine of z similar way. In general, we say cosine of z is 1/2 of e to the iz plus e to the negative iz. And sine of z is 1/2i e to the iz minus e to the negative iz. So these are now complex sine and cosine. Okay. And then also you can define tan of z as sine over cosine, and then cotangent of z as cosine of z over sine of z, which is inverse of tan, and secant of z as 1/cosine z, and cosecant of z as 1/sine of z. And then you see that sine of z prime means the derivative of sine of z is cosine z. How is that? If you take derivative of this equation, becomes what? Becomes 1/2i is constant. E to the iz, you see derivative of e to the u becomes u prime, derivative e to the u. But here, with respect to z, we are taking derivative with respect to z. So it brings an I, e to the iz. And then minus derivative of e to the negative iz brings a negative I. So it becomes positive I, e to the iz. And then you see i's cancel, okay, e to the negative iz. You can see I cancels and get 1/2 e to the iz plus e to the negative iz, which is cosine z, right? And the derivative of cosine is what? If you take derivative of cosine, cosine of z derivative, it means that d cosine of z over dz means derivative with respect to z. Become, sorry?
Either sine of z,
Yes. But I want to show you that. Becomes this. Becomes the I e to the iz minus I e to the negative iz. And then you see that I can be factored and sent to the denominator. So become I/2 times e to the z to e to the iz minus e to the negative iz. And then if you put the I in the denominator, or you can multiply numerator and denominator by I, becomes negative 1/2i, because I squared becomes negative 1 times e to the iz minus e to the negative iz. Sorry, cramping everything. So you see that this is negative of sine z. So the same relationship that we have for in the real functions we have here. So cosine of z prime or derivative of cosine becomes negative sine of z. All right. We stop here and we take it from there the next time. Okay.
So what is